Now you should be quite used to potential energy diagrams, but now we have to look at kinetic energy diagrams. Potential energy diagrams would have the energy up the y-axis, but kinetic energy diagrams have it along the x-axis. So that's one of the things you got to look for. Read carefully. This is called an energy distribution, and what it's saying is, here's our number of particles. So we have no particles with no energy. And as we come along, we have a few particles, lower energy and average. Here's our average. And as we go up to more and more kinetic energy, we end up with fewer and fewer particles. So that's our energy distribution. Key points: the particles do not all have the same amount of kinetic energy, meaning they will have difference in motion. And that's going to be the varied kinetic energy. Now we want to see how we can affect this in two ways. One, what happens if we change the temperature by increasing temperature, adding energy, or decreasing temperature, removing energy. And also, how is it affected by adding a catalyst? So here we look at the effect of change in temperature. Now, you see 25 degrees. This is the curve like so. And then we go to 200 and then 400. And what happens is the peak drops down and shifts to the right. And that means that on average, the particles have more energy than before when they were at 25 degrees. Now this line here represents the activation energy. Remember, energy is going along the x-axis. So initially at 25 degrees, just a very few particles have enough energy to react, have enough energy to make the activated complex. When we get to 200, we've increased that by quite a factor. And that might be in the order of 10 to 15 times greater. How do we tell? We compare the areas. Here it's a tiny area, now our area's gotten bigger. And when we get to 400, all these particles to the right of the activation energy have the capacity to react. And so that's going to be way, way more than initially. And that's what happens. Increased temperature, we shift the distribution to the right, and more particles have the activation energy. Now let's look at adding a catalyst. So we have our energy distribution, and this line represents our initial activation energy, and you can see we have just this small number of particles. This little almost triangle shape represents the number of particles that would be able to react. But what happens if we add a catalyst? Well, the catalyst, there was our original line, now our line is moved over here. A catalyst reduces the activation energy, so now all of a sudden all of these particles have the ability to react. And if we compare areas, this might be about 5 times the area of this, 5 or 6 times. So our rate of reaction, we would expect to go up by a factor of 5 or 6. So that's what a catalyst does. It doesn't affect the distribution, it affects the activation energy. And the previous one, when we change the temperature, we don't change the activation energy. We are pushing the diagram or distribution to the right and getting more particles that can react when we increase the temperature. So watch out for that. When you see energy along the x-axis, it's usually a kinetic energy question.